Hello guys, I'm your TA Balaji and I will be discussing the solutions for assignment 10. Question 1. Which of the following is true for a 12-bit 2's complement number? Basically, we'll have to calculate the maximum value and the minimum possible value for a 12-bit 2's complement number. As you can see here, the maximum value is 0 followed by all ones, as the first bit is always minus 2 power 11 in this case, and hence the maximum value would be 0 followed by all ones. Now the decimal equivalent for that is 2 power 11 minus 1, which gives 2047, and hence option A is right. The next step is to calculate the minimum value. The minimum value, as you can see, is again 1 followed by all zeros, since let's say if you have any other value, let's say 1 followed by all zeros and 1, this will still be minus 2048 plus 1, which is minus 2047. Minus 2048 is the most negative value that you can obtain here. Minus 1 into 2 power 11 is how you calculate this, as this is the first bit. So the answer is minus 2048 and option C is right. Okay. Question 2. 1011 into 101. Okay, so in the options you can see that there are two kinds of questions. One is an signed 2's complement notation and another is an unsigned numbers, right? If they were unsigned numbers. So in the case that they were signed 2's complement numbers, so let's say we have 1011 and 101 represented in 2's complement notation. We obtain minus 5 for 1011 and minus 3 for 101. So minus 5 into minus 3 gives you plus 15. And hence the answer option A is right. Similarly, if you assume that both of these are unsigned numbers, then the calculation for that goes as follows. For 1011, it is plus 11, and for 101, the answer is plus 5. So 11 into 5 is 55, and hence the answer option C is right. Moving on to question 3. Given an n-bit 2's complement number, what is the largest value that can be obtained if the MSB bit is fixed to 1? Right? So if the MSB bit is fixed to 1, to obtain a largest value, all the other bits need to be 1 as shown here. Any other combination will not give the largest answer. Right? So corresponding to this, when you calculate it in decimal, it is minus 2 power n minus 1, and all of this put together is just this. When you calculate what the summation results to, it is 2 power n minus 1 minus 1. So 2 power n minus 1 and minus 2 power n minus 1 cancel out here and giving you an answer of minus 1. And hence the answer minus 1 is correct. Okay, moving on to question 3. Question 4. Given a signed 2's complement number P 1011, if P cross Q is minus P square, then what is the value of Q in 4-bit 2's complement representation? So as calculated here, minus 8 plus 2 minus 8 plus 2 plus 1, right? So the answer is minus 5, and minus 5 into Q is minus 25, right? So Q is equal to 5. 5 in 4-bit 2's complement representation is 0101, and this is the answer, right? Question 5. 1100. If represented in unsigned notation, all that you will do is 01100 is the right answer as shown here, which is option A. And in 2's complement notation, what you can do is you can sign extend beyond it on the left side, right? So hence option C and option D are both right. Both are sign extended versions of 1100. Okay. Moving on to question 6. For a 5 cross 5 array multiplier, how many full adder blocks are needed? So for this question, we can look at an example from the class, right? So for a 4 cross 4 array multiplier, there were 3 rows and 4 columns, which gave a total of 12 full adders if all were full adders. following the same logic, the formula you will devise is n minus 1 into n for an n cross n multiplier, and in this case it will be 5 into 4, 20. Okay, so 20 is the right answer. For a 5 cross 5 array multiplier, what is the critical path delay? Given t and is equal to so much, t carry is equal to so much, t sum is equal to 3. Assume that the multiplier is made using full adder blocks only. Okay, so how do we calculate this? Again, let's go back to the example here and look at a 4 cross 4 multiplier, right? As you can see, the critical path is as shown in pink color here, right? So it is this from here, it goes here, it goes here. This is the critical path. You can see there is one t and here referring to this, 3 t sums, 1, 2, 3 t sums here, and 5 t carries, which is 1, 2, 3, 4, and 5 t carries, right? And hence the answer is as follows: 1 t and plus n plus m minus 3 into t carry plus m minus 1 t sums, right? So by after calculating this, we obtain the answer 27, and 27 is the right answer. Question. We will look at question 8 now. For a 5 cross 5 carry save multiplier with a ripple adder as the vector merge stage, what is the critical path delay? Given t and is equal to 1, t carry is equal to 2, t sum is equal to 3. Right? So again, we will go back and look at what we have done in the class. Right? Here is an example of a carry save multiplier as done in the class. It is a 4 cross 4 carry save multiplier. The critical path is as shown in this direction, and it has 1 t and 3 t sums, 3 t carries, and 1 t sum at the end as shown here. Upon construction, we can devise this formula, and hence for a general case of an n cross m multiplier, right? So when we plug in the values and calculate, we obtain the answer 24. 24 is the right answer for question 8. Moving on to question 9. When performing an n-bit signed 2's complement multiplication, how many full adders will have one of the inputs tied to logic 1, right? So in this case, let's again look at what we have done in class. So we have come to an understanding that there are two trailing ones that are left behind, right? So these two ones, as pointed out here, 2, in the 4-bit multiplication case, the answer is 2, right? So the math works out such that no matter the value of n, there always is 2 number of full adders tied to 1. When you work out another example of the same, you will understand this in even more detail. So always 2 is the right answer here, right? Finally, question 10. When performing an n-bit signed 2's complement multiplication, how many positive partial products and negative partial products exist? For example, as shown in class, for a 4-bit multiplication, there exists 10 positive partial products and 6 negative partial products, right? So now let's look at the equation. So in this equation, z is equal to x into y. For an n cross n signed multiplier, we obtain this formula, right? This and this. So when you perform cross multiplication, we obtain the one shown in pink as the the total number of negative partial products, and the one shown in red as the total number of positive partial products, right? So when you look at these numbers 0 to n minus 2, so basically you have n minus 1 plus n minus 1 number of positive partial products, which is 2 into n minus 1. And when you look at this, is again 0 to n minus 2 and 0 to n minus 2. Here it is, so n minus 1 the whole square, and again plus one more partial product, which is plus 1. So this is the total number of positive partial products. So hence answer option B is right, and the total number of negative partial products is 2 into n minus 1. So option A is also right. Now we also know that n square is the total number of negative plus positive partial products, and hence the total number of positive partial products is also n square minus 2 into n minus 1. Basically, it comes out from this formula. N square is equal to the negative plus the positive. So again, if you represent positive in terms of this as well as this, you will get n square minus 2 times n minus 1. And hence option D is also right. Thank you for your attention. Thank you very much.